screen in a moment. Okay, so welcome to Astronomy on Tap in Leiden, coming to you live from a few different houses in different places in Leiden and elsewhere in the Netherlands. I want to say a very warm welcome. I think we have some people not from Leiden joining us tonight, so great to see you virtually. We're not at the Bercht, but it is 30th of March, and we have an exciting program with two speakers here going to be talking on topics about active stars from our sun and how it induces space weather. That'll be Carl Shneider, and then Aurora Kesseli talking about active stars, activity in low mass stars and how that might affect planets around them. So without spending too much time on an introduction, for those of you that don't know, Astronomy on Tap started in New York City in 2013, so that's 7 years ago. They'll actually be celebrating their 7th birthday coming up in April, so keep an eye out for that. It spread from there and now is currently in over 40 locations all over the world. Leiden was the first one in the Netherlands, and it started 3 years ago this month, so this is our 3rd anniversary, and we're very happy to share it with you tonight. So join me and say cheers. I hope you have a beverage of your choice. Some of us have Astronomy on Tap glasses from all over the world, so cheers. As you all have noticed, if you're live with us, we're streaming live from Zoom to YouTube, so you can hear the talks tonight, and you can watch it even afterwards. If you're watching live, you should be able to leave questions for the speakers in the chat on YouTube. And then we'll get a moderator to ask your questions. And just in advance, if we have lots of questions and your question doesn't get asked, apologies for that. Also, let us know that you're watching. Say hi, tell us where you're from, if you're happy to do that. And also interact with us on social media. We're on Twitter, Instagram, and Facebook. And just on that note, here's how you can reach us on Astronomy on Tap in Leiden on Facebook. That's where we share details of our events. Also on Twitter, you can talk to us, and Instagram, both at AoT Leiden. Our YouTube channel is on the top there. Also on our website, Astronomy on Tap.nl, you can sign up for the newsletter on there, or you can email us directly. That's on the bottom of this page here, Astronomy on Tap, leiden@gmail.com. So we start every event with a little bit of astronomy news. So here's something exciting. Just recently, this comet 2019 Y4 has since been called Atlas after the survey that detected it. This comet was detected and they've been watching it closely. And they think that it should become fairly bright. In fact, might even become as bright as which, like, the early evening side is like a spectacular sight to see it near the newish moon. But this comet should come to its closest approach to the Earth at the end of May, on May 23rd. Before 7 days later, May 31st, it'll make its closest approach to the sun. Now, it might become very bright, in which case you can see it with your eyes, and that will be fantastic, which would be very disappointing. But you should be able to right now, maybe even see it with binoculars. It might be a bit faint, but you can also see it with a small 6-inch telescope. In some other news recently, this is just something that's quite local to the Netherlands and Europe, actually. We have a telescope called LOFAR that's situated mostly in the Netherlands and other European countries. And we've been doing a survey with this telescope. And there's a big citizen science project that we released to the public earlier this month that allows members of the public to help us in finding which radio sources match to. So this will help with scientists to understand how supermassive black holes and galaxies grow and evolve in the universe. And we really need lots of people to participate. Okay, so what's up for tonight? Tonight we have two speakers for our usual Astronomy on Tap regulars who come down to the Burgt. I think many of you come for the games as well. Unfortunately, tonight we won't have any games until we figure out how to do that in a remote way. Maybe next month we'll do something. So we'll just have the two talks. Carl Shneider up first, speaking about space weather in our solar system. And then after that, we'll take some questions from the YouTube chat, and Anik will ask them. And then after that, we'll move on to Aurora, speaking about big flares on small stars. And then we'll take questions from her, and then finally we'll wrap up. So our first speaker, Carl Shneider, originally did his PhD in Leiden Observatory here in Leiden, working on magnetic fields and galaxies. He then moved on to the UMC in Utrecht, and he worked on something quite different, using machine learning to, I forget exactly what it is. I don't have my notes up next to me because I just have the screen. But since then, he's moved on to the Centrum for Wiskunde and Informatica in Amsterdam, where he's been working on space weather. He does a lot of machine learning in his work, and hopefully he'll talk a little bit about that tonight. An interesting fact is that last year he was selected to be part of the Frontier Development Lab, doing some kind of SETI research. So maybe we'll ask him something about that at the end of his talk. So without further ado, we will switch over to Carl and his slides.
Thank you, Wendy, for the warm introduction. I think the slides will come up in just a moment. Yes, thank you, great. Okay. Perfect, so I can use this now, right? Great. Okay, yes, so thank you for the warm introduction. Thank you for this awesome invitation and for very awesomely organizing this remote Astronomy on Tap Leiden. It's really cool. So without further ado, this is our sun, our beautiful sun, this giant ball of dynamic plasma that gives us life and warmth, and also is a very dynamic star. So we're living with our star. And as we can see here, this is actually a time-lapse video. This is sped up. The normal rotation of the sun takes 27 days. So that's basically like one Earth day. And this has been sped up through actual images from satellites that have been taken. And as you can see here, there are many different phenomena that happen. Prominences, solar flares, coronal mass ejections, everything to do with plasma and the magnetic field of the sun. So the sun is huge. It's a very big plasma ball, and we'll see just how immense it is. So I'm Carl Shneider, working at the Centrum for Wiskunde and Informatica, and my topic of research is space weather and machine learning. So as you can see from the picture, you already probably know what I'm going to speak about. If you're wondering how you came to that thought, you've been using the force. So what we see in this schematic are prominences and also magnetic fields. So open magnetic field lines, closed magnetic field lines. You see this enormous eruption of plasma that's being hurtled off from the sun. And in this case here is being hurtled toward the Earth. So you also see schematically radiation coming off the sun in terms of these wavy particles, schematically depicted as wavy particles. And then we'll get to an explanation of what actually the rest of the schematic is showing. But it's showing magnetic fields, basically. And in this talk, the force will be the electromagnetic force, mainly the magnetic component of that force. We're going to briefly preface this with a story. So please read along with me. All right, and now may we have music, please? Sorry?
Yeah, now it is. Sorry, because I was muted. Yeah.
Oh, sorry. We've skipped ahead, so
I can.
I won't slide.
You have control, right?
No. Oh, no.
I have it. Okay.
Okay, yes, yes. Now I do.
Okay, great.
Thanks.
No
Thanks.
worries.
Thank you. Great. Yes. Great. Thank you. So that's a preface to this journey today, this story. Thank you. Great. So actually, this story begins earlier. So we go back to this very historic event called the Carrington event. It happens on August 27th, 1859. Sir Richard Carrington, an amateur astronomer in the UK, was observing the sun and happened to see an ominous group of clouds on the surface of the sun, which was quite unusual. So he decided to draw them in his notebook on that day. And not only did he see this large ominous grouping of clouds, but he also saw a very bright flash as well. As you can see here, this is directly from his notebook on August 27th, 1859. It doesn't seem like much, but if one considers it further, if you see the extent of these drawings, it's from minus 20 degrees to plus 20 degrees above the equator. That's quite a large radial extent if you consider the Earth going from 20 degrees north to 20 degrees south. That's quite large extent. And we're talking about the surface of the sun here, which can accommodate 1.3 million Earths inside of it and 109 Earths across its diameter. So this is very big. So in this time, 1859, there wasn't any of the modern technology that we have now. They had telegraphs back then. And as you can see here, these are the telegraph wires and the telegraph devices that were used. And on that day, and on the storm that arrived actually a few days later, on September 1st and 2nd, 1859, basically people as far down south as Cuba, as Mexico, could see auroras in broad daylight. So basically, it was evening time, but it was just as bright as day. And one could just see auroras just with the naked eye, broad daylight. One didn't need the deep dark conditions in in very high northern latitudes to be able to see beautiful auroras happening. And actually, at that time, also the telegraph operators, many got electric shocks when they were transmitting telegraphs, and many telegraph lines actually caught fire. So something very, very strange happened on that day, and it was noted all over the world. All over the world, people saw and experienced very interesting things. So mainly electric shocks and auroral displays at midday. So what actually happened on that day is, we believe, akin to something that happens much closer to us, mainly in the event mentioned in the Star Wars trailer in 2012. So this is, I think, do I have control of the slides? I think may I, oh yes, thank you, great. So mainly this is what happens. There was a very large coronal mass ejection that followed in conjunction with the solar flare that Richard Carrington observed. This is what we see here. This is billions of kilograms, billions of tons of plasma being ejected from the surface of the sun. And we'll see soon enough how large in space this actually is. But bear with me for the moment. Just imagine that each one of these dark spots that you see here and the bright ones, you can accommodate easily one full Earth inside of that. So here you have a bit of a zoomed out picture. You can see really the chromosphere of the sun here at a particular wavelength. This is really the photosphere is what you would see where the photons come, but here this is where most of the plasma you can see in terms of the chromosphere. Here you have the coronagraph image of the sun, which is a plate on a satellite that blocks out the sun so you could see what's happening around the rims. And you see how large this ejection was, how big in degrees this was. Here's a further zoom out going to Lascaux C3, which is another coronagraph, but from a satellite that's a bit further out. And there's a metal plate blocking the sun again. So these two images are now superimposed, and you see the full enormity, a full extent of this enormous plasma explosion. So as promised, this is how that particular plasma explosion looked like in comparison to Earth. Earth is just like a pearl inside of this large ejection. So thankfully, Earth is quite far from the sun, 150 million kilometers. So it takes light 8 minutes to reach us. So this is the distance is not correct here, but the relative size is. So this is how massive these explosions, these CMEs are, and how large events on the sun are as well. Here is a beautiful composites, beautiful images taken at different wavelengths of the same event. So not only are they beautiful to look at, but they also reflect, if one looks carefully, different characteristics. They are sensitive to different kinds of elements that give off different heats at different wavelengths. So they're showing you different properties of the plasma. So I think here in the blocks here below, we'll see a bit later that this is I think the most hottest temperature, around 10 million degrees, really sensitive to the corona of the sun. And then you have more cooler temperatures, such as the chromosphere here in red, and also like the photosphere here in yellow. So one can discern, if looking carefully, different kinds of properties and characteristics. That's why multi-wavelength astronomy is done on the sun as well, for the sun as well. So what drives all of these events? Well, it's really the magnetic fields. So magnetic fields are ubiquitous in the universe, and our sun is no exception. So there's a large-scale magnetic field and also small-scale magnetic fields, and they basically drive through a process called the dynamo mechanism. They drive all of these eruptions that take place. So basically, you have sort of like stretched rubber bands that have tension in them that rise up to the surface due to their magnetic pressure. And then as they rise, they pull up plasma with them, and then they can stretch out or even break and reconnect, releasing this plasma as if it was a rubber band or a slingshot, just hurling this plasma into space. So here we have a simulation, actually, which is done over a time period of several months. And it shows how dynamic the sun really is. So the colorful lines are the open magnetic field lines that come out from the surfaces of the sun, and the white lines correspond to closed magnetic field lines. The dark spots that you see are actually the sunspots that we observe in the sun. And what you can see is how the magnetic fields interact with each other and how they're reconfigured. It's sort of like a switchboard that's being continuously reconfigured in space. And all these reconfigurations cause these releases of plasma, these flares, these coronal mass ejections, these prominences. So it's very dynamic indeed. And when you see a sunspot, actually, they always occur in pairs, because the foot point is where the magnetic field comes out, and then the other foot point is where it comes back in. So you always have sunspots coming in pairs of opposite polarity. So they originate in the northern latitudes, then as the 11-year regular cycle of the sun, it's an 11-year cycle, and every 11 years the polarity flips from north to south. And during the 11-year cycle, you have sunspots that start forming in northern latitudes high up, and then they drift down to the pole. And then we can see these if you have prolonged sunspots or prolonged coronal holes. You can see them again 27 days later, because that's 27, 28 days later is the average rotation along the equator, and it's like 30-something days at the poles of the sun. So what we have here is a measurement of solar activity. So solar activity is actually measured in terms of sunspot number. And actually, people have been going out ever since telescopes were invented and actually looking up, not directly at the sun, but using telescopes in order for the telescope to cast light on a sheet of paper, let's say, and then to actually count the number of sunspots that they see. Official records, cycle 0, actually begins in 1750, and it's an 11-year cycle. So you see here it grows and then falls back down, grows again. It's periodic, roughly 11 years. And now we're actually basically at the start of cycle 25, as you can see at the bottom plot here. So you have sunspot number on the y-axis and dates on the x-axis. So right now we're in a quiet sun period, but also during quiet times there are solar flares and even sometimes coronal mass ejections. So what do we mean by solar activity and sunspots? So let's say at the beginning of a cycle, let's say here it's shown cycle 24, the cycle we're at the end at, and we're at the beginning of cycle 25. But here in 2008, the sun was pretty much quiet, so not that many sunspots. This is probably, the image is probably like the most active the sun was in that year. And then progressively, as the cycle goes on, about halfway, about a few years later, 3 years later, you have already peaking activity. 4 years later, 2012, 2014 is the peak of the activity, and you can see visually how active the sun now is. So it really has woken up, and then it again starts to become more dormant, less active as the years progress. And in 2017, it's again pretty much as quiet as it was in 2008. So I mentioned multi-wavelength astronomy, and the sun is observed at all these different wavelengths. And by observing at these different wavelengths, we also probe different depths of the sun. And also each of these wavelengths corresponds to different temperature. So at the bottom row and on the right-hand side, you see 131 angstroms. This is the wavelength that's used, and it corresponds to 10 million degrees Kelvin. That's very, very hot. It's even hotter than the surface of the sun, which is like 50,000 Kelvin or 600,000 kelvins that you have here. Even as you get to the corona, it's much hotter than the surface of the sun, which is very intriguing, actually. That's quite counterintuitive to a normal object that you would encounter. So you have very high temperatures in the corona, and that's thought to be due to magnetic friction. And at all these different wavelengths, you can see different properties and study the sun at different properties. So for instance, at the photosphere, the HMI continuum, that's in terms of white light. So that's, if our eyes could look at the sun directly, don't do that. But if they could, then this is what you would be able to see, these sunspots, so the HMI continuum. Next, so what we have here is we actually live inside of a bubble that's carved out by our sun, and it's called the heliosphere. So Voyager, as you may know, took about 30-something years, maybe 32 years, to actually leave the heliosphere and actually venture into interstellar space. And by the heliosphere, we mean this, that as the sun, as this giant ball of plasma is rotating, it actually, because it's rotating and it has constant also solar wind coming from it, it drags this plasma across, forming a ballerina skirt. So this ballerina skirt is also like an Archimedes spiral. So imagine a ballerina pirouetting and her skirt going round and round. And this plasma sheet, because a changing magnetic field induces a changing current, this current sheet is about 10,000 kilometers thick at the location of the Earth and stretches out way beyond our solar system. So here you see Pluto's orbit, but it stretches far beyond. And it's known as the heliosphere. So it's really this giant bubble that encases our entire solar system, also shielding us from high energy particles coming from even outside of our galaxy. So this is how this ballerina skirt, this current sheet looks like from the sun. So you can see how wavy it is and how dynamic it is. So the Earth also has a magnetic field. Luckily for us, not every planet has a magnetic field. The magnetic field is facilitated by a movement of molten plasma that's differentially rotated, and that induces currents and then a magnetic field to appear. So this is an idealized Earth field. So it's a dipole, known as a dipole field. Also, the sun has a pure dipole field, but also it's more dynamic on smaller scales. So this is how an idealistic Earth magnetic field would look like. And we'll see how it actually changes due to the magnetic pressure of the sun. But thanks to this protective magnetic field, it actually acts as a shield. It shields us from everything that's coming from the sun, from these highly energetic particles. So the sun being as massive as it is, it's basically like a tsunami wave that's coming to the Earth, and the Earth being like a pebble on the beach. So here we see first Venus, which doesn't have a magnetic field, maybe a very weak one. And you see that as this solar storm, as it passes, it strips any kind of atmosphere from Venus because it's not protected by any magnetosphere. So there's no chance of actually having water or any other kind of more complex chemistry because of these highly energetic particles coming through. And here you have this enormous tidal wave as it comes to the Earth. And because of Earth's magnetic field, which acts as a shield around it, you'll see that Earth is now sort of like a blue marble in this current of very highly energetic particles. You're beginning to see now the silhouette of these particles being deflected around the Earth because of this protective magnetic field. Some of these particles do manage to enter the Earth's protective areas and form sort of this plasmasphere around the Earth. And some of these even cycle into the poles and giving us the beautiful auroras, as we'll see in a moment. But first, schematically, this looks like this. This looks like a Tai Chi colors, a little bit, maybe like a Dragon Ball Z comic, but this is real. So what's happening is that there's coronal mass ejection, so the magnetic field is being stretched out, it's lifting, it's carrying this plasma with it, and it's approaching the Earth. And because of this magnetic pressure, it pushes this perfect dipole, as it would be. It compresses it on the day side, where the Earth faces the sun, and it elongates it on the night side. So you get this bow shock, which you see as this large curve, and this defines the magnetosphere. And then on the back of this tail, so you see it looks like a spider almost. This design looks like a spider. On the back, these lines connect, and then these particles that have already passed, they can gyrate around, and then they gyrate into the poles. And we'll see that after this slide, but first, this is what comes at us from the sun. Not only is it light that gives us warmth and radiation, but there are also flares, so a lot of X-rays come. Also energetic particles that have mega electron volts. Also, you have the solar wind, which is constantly coming at us at 450 kilometers per second, around 1,000,000 miles per hour, and that takes around 4 days. But there's also strong solar wind that comes when there's, let's say, a coronal hole that's pointing toward us, and that can go up to even 1,200 kilometers a second. So when there's a strong magnetic storm, that can take around 10 hours. So you see there's like a lot of complex phenomena that can come toward us, and all of this has a different time windows of arrival at Earth. And it's important to know as a forecaster, or for forecasting purposes, in order to alert satellite operators and power grid operators on Earth, when we expect this to happen, just as in regular weather on Earth. You know, when is it going to thunder? When is it going to be a heavy storm? So what we see here is this radiation in the form of coronal mass ejection coming. And what you see here, you have this protective shield just being cut through, because this magnetized plasma can have an orientation of the magnetic field that's opposite to Earth, and so it can pierce through this plasma. So what you just saw, maybe I'll put this on replay again, is you have this explosion of very hot billions of kilograms of plasma. It's able to penetrate the first layer, let's say, because this magnetic field is oriented opposite to the Earth. And then the other particles go around, and then they spiral back in on the night side. And then it gives us these beautiful auroras that we see. And the stronger the storm, the lower the auroras will be. So like in this Carrington event, people could see auroras as far down south as Cuba or in Mexico. So you see, like the aurora was even possible to see there. And this is a view from the ISS, from the International Space Station, of how the aurora looks like. And all this radiation from the sun, all these storms and plasma that comes from the sun, it has an effect on our modern society. So it increases Dragon satellites. So satellites might need to either change orbits, or they can get damaged, so they might need to be switched off. This can affect communication, telemetry, this GPS, GNSS. Astronauts need to be alerted because there can be fatal doses of radiation. Also, there can be interruptions in radio communication, which is also very important. Airline passengers can receive more radiation than they are used to, than they need to be. There could also be radio wave disturbances. And also on Earth, there can be induced currents, so there can be blackouts. There's a famous blackout in 1989 caused in Canada, which took only like 90 seconds to last 9 hours, and 6 million people were without power. There are also induced currents in the ground, and also under the sea. So this really affects pretty much everything, all technology that we have. And so that's why we've created all these satellites and monitors in order to study the sun and try to predict its effects and understand them better. So you have satellites, for instance, like the MMS that is studying the magnetotail of the Earth. You have ICON and GOLD, which are studying the day side. You have SDO and SOHO that study the sun and that give you these beautiful images of the sun. And then you have the Parker Solar Probe that just launched this year, and also the Solar Orbiter, which are flying really near the sun and actually are flying outside of the Earth's protective magnetic field. And also Voyager there that ventured outside of our solar system. So to briefly mention, all this data that's coming in from all these satellites and all these observations is very useful for something that we call machine learning, which is a subset of artificial intelligence, which you've probably heard about. And so artificial intelligence, machine learning, and deep learning, which are subsets of that, is very good at finding patterns in data. So the more data we have, the more coming from images of the sun, coming from time series data, from energy levels, from temperature, from electron temperatures, proton fluxes, energies, feeding all of this into a machine learning system can really leverage a system that can try to forecast when such a storm will come about. And so a Carrington event in modern times might look like this. This is an artist's impression. So auroras in broad daylight affecting transportation, everything that was mentioned, satellites. We're living in a modern society, so this is how we operate today. And if in the event of a very serious storm, we don't want to be in this state. So it's very important to have these forecasts. And then there's a current forecast for cycle 25, which I think has just started. The first sunspots have been observed. And this cycle is also predicted to be pretty low. So cycle 24 was not so active, and so cycle 25 is believed not to be too active. So that's good news for us in terms of technology. But also during quiet times, there might be solar flares that can be quite strong, and also coronal mass ejections. So stay tuned to solar cycle 25. May the magnetic force be with you. And just a quick photo. This is Neil deGrasse Tyson. And this is a free ebook also from NASA. So they please check this out. Very beautiful pictures and information. Thank you.
Woohoo! Amazing. Thank you, Carl, for this amazing talk. We've already had some questions coming in. So I'll start asking you the questions that we have, but for everyone listening, the live stream is lagging a few minutes. So if you fill out the questions on YouTube now, then we'll still be able to ask those to Carl. So the first question was from BVD Vorn, and the question is, how did they measure the solar spots in 1750?
Yes, very good question. So that's with the invention of the telescope. So Galileo invented the telescope, and also someone else possibly around the same time as he did. And what you can do is you can allow light to come inside of the telescope, and then you can project it down on, let's say, paper, and then you can view the sun and what's happening on it. And then you can count the number. You can actually physically count sunspots. So that's I think what people did. So this was a day-to-day job. So very dedicated people counting all of these sunspots for us. That's wonderful because we have a very long record now. So even from the early 17th century, there's records, but officially it started in 1750. But that's how people did it. This gives us a very, very, very long history of these solar events. Also from tree rings and also from certain kind of magnetic minerals. We can also have a recording of severe storms that have affected Earth. So we also have a geological record of storms. And so we can compare that record with a geological record too. Thank you for your question.
Okay, great, thanks. Then we have a question from Alex Critland asking, does the dip in activity in 2013 have any physical reason, or is it just detection noise?
Very good question. I don't know it by heart. 2013, you say. So that was the prognosis that we just saw, right? I'm just getting to it. 2013, there was a dip. Yes, so they're non-uniform. So the sun is a highly dynamic plasma ball, and there can indeed be dips during even maximum. So if you would draw like a mean curve, then indeed you would see more homogeneity. But in terms of real numbers, you can have fluctuations in sunspot numbers. So that's just due to the complicated nature of the magnetic fields. Yes, that would be. Of course, there's also noise, as you mentioned, in instruments for sure. But in terms of sunspots, you can. That's one can readily tally them. I mean, there can also be disagreement. Sometimes if if a sunspot is too small or doesn't last a particularly long time. On average, sunspots can last from days to months. So there can also be smaller, shorter-lived events that might pop out and in. But regarding this plot that you referred to in 2013, there is indeed a dip, and that is due to the complicated nature of the magnetic field of the sun. The cycle 25, the curve looks homogeneous there because that's a prediction. So they haven't measured anything yet. Yeah.
Okay, thanks. Then the next question is from Hannah Gray, and she asks, do any other planets have magnetic fields?
Yes, thank you for that question. Indeed, they do. Most of the planets in our solar system have magnetic fields. Jupiter has a very, very strong magnetic field. It's even so strong that one of its moons, I believe, Io, experiences like how do you call it? The magnetic field can rip off or ionize particles even on the moon. So it's very strong. I think it's the second strongest after the sun in our solar system. There are a lot of objects, also exotic objects like pulsars and quasars, that have very, very, very strong magnetic fields. That even magnetars, I think, have the strongest field. So if a magnetar were to be brought in at a distance of where our own moon is, everyone's credit card would lose information. So these are how strong that magnetic field is. In terms of magnetic fields, let's say in a laboratory, like laboratories, for instance, in IMEC, can generate 7 Teslas. That's way more than what's on the sun. But the sun, like the sun's, the regular magnetic field in the sun, it's comparable, let's say, to not in sunspots or coronal holes, let's say, which are many thousands of times stronger. But in normal sun activities, the magnetic field is not very strong, but it's very big. So the fact that it's very big and its extent is very, very wide, going outside of our solar system. That's what drives all these activities. So not the strength, but really the structure of the field and the extent of the field itself.
Okay, great. Then the next 2 questions, I'll take them together.
Okay.
From Leonard and Tom, how do you predict solar cycles, and on what type scales can you predict the sun weather?
Excellent question. Excellent question. So there are ongoing efforts right now. There is a community leaderboard from NASA called the CCMC, I believe. I have to look that up, but there's a community leaderboard from NASA, and they track predictions. And I think the current prediction is off by 6 hours, I think, or even 10 hours. So the current there are many efforts to track this, and it's very difficult to do that. So you can, what works best, sort of that's used widely in models, is to just expect what you've seen previously. So in the past few days, expect the same weather to reoccur again. But that, of course, doesn't account for rarer events like flares or coronal mass ejections. So those kind of models would miss these kind of events, but they would be good in describing, because the sun is for the most part quiet, let's say, even in the active cycles, relative to how many flares there are, how many X-class flares, which are the highest category there are, they're not that many. So it's more difficult to predict these rare events, and for that you can use machine learning, different statistical methods. So what we're doing in our group is we're trying to have a forecasting window of 3 to 5 days ahead. So there are efforts that are going on from different groups around the world that try to give a several day ahead heads up. So something like, let's say, 20 hours or 24 hours would be already a good heads up, because as we saw, it affects satellites, it affects power grids. So if you could give a power grid operator or a satellite operator this heads up, with more time, then you would be able to save the satellite or save people from a blackout. So there are a lot of different approaches, a lot of informatics, a lot of different machine learning approaches, information theory, Bayesian statistics, Gaussian processes, a lot of different approaches that people have used and are continuing to use. So the more data, the better. So we have more satellites coming on, also more missions planned, and with more data, more points of observation, we can establish those patterns better.
Okay, thank you. Then I think we'll go for our last question from Tuan. How excited are you for the solar orbiter, and how will this influence your work?
Very excited. Yes, great that you're on board with these developments. Yes, very excited. It's wonderful that we have this awesome mission, Parker Solar Probe. It's flying the closest to the sun than we've ever been, and it will send a lot of new data toward us. It will be able to study also the high latitudes, so what happens at the poles of the sun, which influence the next solar cycle. So it's very crucial to have this sort of overview of the sun. Literally, that you're looking at the poles, because from Earth's orientation, you can really look at the equator of the sun, and you can look at, let's say, maybe 60 degrees latitude, but you cannot see further than that. But if you have a satellite like the Parker Solar Probe that's positioned, that can also fly over the sun or thereabout, then you can have very, very nice views of the entirety of the sun, and then that's really useful for predicting next cycles and how, especially during field reversal times, during the end of an 11-year cycle and the beginning of a new one, the sun's magnetic field goes really haywire, and there are very interesting effects that occur, especially this ballerina sheet that we saw. It goes very wobbly, and a lot of complex plasma physics happens, and a lot of complicated physics in general happens. And so with this influx of data, I think for sure models will be better. Especially there are a lot of space weather prediction centers around the world, like NOAA in Boulder, Colorado, Shrepsey, the Space Weather Prediction Center. You have KNMI in the Netherlands. You have also Space Pole in Belgium. You have in Finland, in Japan, in other countries around the world, China, India. So yeah, there are weather prediction centers, space weather prediction centers around the world.
Okay, thank you very much. Then I think we are moving on to the next speaker.
Thank you.
Thanks again.
Thank you.
Great. Thanks, Anika, for moderating the questions. And thank you very much, Carl, for that interesting talk. Apologies for the delay in getting the sound actually working on your videos. But yeah, thank you for joining us. Okay, so next up, we have Aurora Kesseli. Let me just share my screen again briefly. Okay. So Aurora is a postdoctoral fellow here at Leiden Observatory. She is working on trying to detect the signatures of different molecules in giant exoplanet atmospheres. So these are massive planets around other stars. Before she came to Leiden, she was doing her PhD at Boston University in the Institute for Astrophysical Research, where she worked on something a little bit different in looking for magnetic activity and chemical abundances in lower mass stars. An interesting fact about Aurora is that she really loves baking. Welcome to the club. But she has in fact won a small baking competition, which I can't say the same of my own baking. So Aurora is going to be talking about the magnetic environments around low mass stars. So thank you, Aurora.
All right, great. Thank you so much for the introduction. And now let's see if I can share my screen successfully. Okay, great. So thank you so much for the introduction, Wendy. And I'm really excited to be at Astronomy on Tap, even though it's virtual. I have my beer here in my Astronomy on Tap cup. And today I'm going to be talking about flares on low mass stars. So that was a really great introduction to my talk that Carl gave. So I'm basically going to be talking about a lot of the same type of mechanisms that he talked about, so flares and coronal mass ejections, but just on a different type of star, and what we expect to be different, what we expect to be the same, and how this might affect planets that orbit these stars. And like Wendy said, I currently study exoplanets, but I did my PhD on low mass stars. This is a perfect joining of my current field and my previous field. So just to start, I wanted to give a brief introduction about low mass stars. So I've been calling them small stars, but you might be wondering how small is small. It's all relative. So on this slide, just a really basic introduction. So the yellow circle is the size of the sun, and then the other circles I've scaled to be the sizes of these small stars. So the biggest of the small stars is about half the diameter of the sun. And the smallest one is about 10% the diameter of the sun. And an interesting fun fact is that that's actually about the same size as Jupiter. And so you might be wondering, well, then why isn't Jupiter a star? These small stars, even though they're the same size as Jupiter, they have masses that are almost 100 times that of Jupiter. And so you have all of this mass condensed into a really small space. And so you get really high temperatures and really high pressures, high enough to fuse hydrogen into helium. And so these are stars because they shine. And Jupiter does not have as much temperature and pressure in the center, and so it doesn't shine on its own. These small stars have masses that are between 10% for the smallest and 50% of the sun's mass for the largest. And they're a lot dimmer than the sun. And so the smallest ones have brightnesses that are only 0.02% that of the sun. And the biggest ones only have luminosities or brightnesses that are about 10% of the sun. And so they're a lot dimmer than the sun is. So next, to describe them a little bit more, I thought I would talk about temperatures. And temperatures in astronomy are not what you're used to when you look at a sink. On the sink, you have your blue faucet, which is cold, and your red faucet, which is hot. And that's wrong. Everything about that is wrong. What you really should maybe think about is something that's a bit more physical when you think about temperatures. And if you've ever seen a flame up close, at the very bottom of the flame, there's a little bit of a blue part. And then as you move farther away from the flame, the color gets a little bit redder. And in the middle, it's maybe a little bit white. And this is actually a lot more physical. And this is similar to what happens in stars. So the largest stars are really big, really bright and blue. And the sun is kind of in the middle. It's this yellow one here. The sun is an intermediate mass, intermediate brightness. And the stars that I'm talking about today are these red ones. And so they're cool in temperature, and also they're awesome. And they don't have much mass, and they're a lot dimmer than the sun. And oftentimes people in astronomy call them red dwarf stars because they're small and because they're red. So even though they're small, They're really important to study because they're everywhere. In our solar neighborhood, so if you look at all the stars within 32 light years from the sun, you can get this census here. And so over here are the hotter, bluer stars. And within this solar neighborhood, there's maybe 10 of them. And for sun-like stars, there's more of them, but still there's only about 100 or so. And these cool small stars here, there's upwards of 250 of these within the solar neighborhood. And so these type of stars make up 70% of all of the stars in our solar neighborhood. And the closest star to us is Proxima Centauri. And that's actually one of these small red stars. So I've just been telling you about how they're small and how they're dim, but not everything about these stars is small and cute and unimposing. They actually have surface magnetic fields that we've measured on a bunch of the nearby ones that we measured to be 1,000 times or even more, a few thousand times stronger than the surface magnetic field of the sun. And so like Carl was just talking about, the magnetic field is really the root of coronal mass ejections and flares, these kind of intense energetic events. And so with surface magnetic fields thousands times stronger, you can have these really crazy, intense environments around these stars. And so I have a picture here where we have Scooby-Doo and the Magnetic Monster, and I've placed a nice picture of a red dwarf star on top of the magnetic monster because these can have really dangerous effects. And you can see I've spent my quarantine time really productively here. And so we don't fully understand exactly why these stars have such strong magnetic fields, but we can get a kind of idea about this just by thinking about how stars and planets generate their own magnetic fields. So stars and planets generate their magnetic fields through the dynamo mechanism, which is a really cool word that I like. But basically all it, in kind of a general basic sense, a star is made up of hot, electrically charged plasma. And this plasma is moving all around because the star is rotating, and also because the star is convecting, which just means that there's particles and blobs from the inside of the star moving to the outside of the star. And all of these motions together, combined with the electric plasma, creates a magnetic field. So you might remember from intro physics class that magnetic fields are just created from currents. And that's exactly what's happening. And while this is kind of a really basic picture, it can still help us get some intuition about magnetic fields and stars. And so intuitively, you might think that a star that's rotating faster would have a stronger magnetic field. And that's exactly what we see. And so the rotation period of a star is not just random. The rotation period actually changes as the star ages. And when stars are born, they're born over here near zero age in billions of years. And they have really fast rotation periods. And so the star is spinning really quickly. And as the star ages, the rotation period gets slower and slower. And here, this is the sun, which has an age of about 4.5 billion years and a rotation period of 27 days. And so this is what our age versus rotation period plot looks like for sun-like stars. For low mass stars, it's a little bit different. And we don't exactly know if there's a single curve or if all low mass stars behave the same. But what we think happens is that for these really low mass stars, they stay spinning fast for a lot longer. And this could be, we're not exactly sure how long, but it could be even up to 5 billion years where they stay with rotation periods less than 5 days. And so what that means is that a lot of the low mass stars that we see near us have rotation periods of less than 5 days. So a lot of these low mass stars are rotating extremely quickly and have very strong magnetic fields. And this rotation can last for 5 billion years. And so these strong magnetic fields can also last for 5 billion years. So hopefully you believe me now that low mass stars have strong magnetic fields. So now we can talk about what are the consequences of these strong magnetic fields. And I'm just going to briefly mention 4 of them, but there's a lot more consequences. So the first one is star spots. So like Carl said, the star spot, which I'm showing in the bottom panel over here on the left, a star spot happens where the magnetic field attaches to the star. And you kind of see this darker region. And on the sun, the star spots only take up a few % of the surface. But on low mass stars, where we have really strong magnetic fields, we think that the star spots can take up to 50% of the surface can be covered in these. Another consequence we think that happens is that these really strong magnetic fields actually cause the radii, or the sizes of the stars, to be bigger than we expect them to be based on models. And then the last 2 are what I'm going to be focusing on for the rest of the talk. And these are really large flares, and flares just light being emitted from the star. And also coronal mass ejections, which Carl mentioned as well, which is just particles being emitted from the star. And over here, I have a nice picture of a flare. And for my PhD thesis, I actually studied how star spots can appear on these low mass stars, and also how the radii are changed. So that's my area of expertise. So I have a quick video that shows the size of a flare that can happen on these really small stars. And so they're going to show a flare on the sun, and then they're going to show a flare on a low mass red dwarf star.
C, M, and X, the largest. An X45 flare is a very powerful flare. DGCVN's flare, however, was much larger.
We can estimate how big the flare on DGCVN was with respect to the solar scale. It would have been an X100,000. So this is several orders of magnitude larger than the biggest solar flare we've ever seen. The flare that Swift triggered on from DGCVN was only the beginning of what turned out to be a fairly extended series of flares, a flare event, if you will, that lasted almost 20 days.
Okay, hopefully you could hear that. Yeah, so the flare on this red dwarf star was orders of magnitude larger than anything that we've ever recorded on the sun. That could potentially be really bad news for planets orbiting these stars. The flares and the particle ejections can erode away the atmosphere. And if these stars have rotation periods that are less than 5 days for 5 billion years and strong magnetic fields for 5 billion years, what this means is that they're going to be experiencing intense flares and coronal mass ejections for billions of years. Here I have a nice picture where I've added cartoon eyes to the star to show that it's being really mean to the planet and blowing its atmosphere away. And we've actually seen evidence of this in planets around other stars. And we've seen these comet-like tails that are coming off of planets that is basically from part of the atmosphere being eroded away. So now I just want to have my obligatory aliens slide because I think everybody likes to hear about aliens. Talking about whether atmospheres around planets are important for life and what life needs to survive. So first, we think that life needs a rocky planet to survive. And around these low mass stars, rocky planets are really common. We actually think that they're more common around low mass stars than they are around sun-like stars. And so we need some sort of surface for life to live on and not a gas giant planet like Jupiter. Okay, next we think that life needs liquid. On the Earth, this is liquid water. And so water kind of gets all of the heavy molecules and stuff floating around and interacting so that we can build larger molecules that you need for the building blocks of life. And also we think that you need an atmosphere. An atmosphere, first of all, it helps to keep water in its liquid form on the surface. Without an atmosphere, there's not as much pressure and it won't keep, liquid water might not stay in liquid form. And also it helps to regulate the temperature and redistribute heat all around the star. And so we think that an atmosphere is important for life. So you might be thinking that, well, this makes it seem like we probably won't find life around these low mass stars, but maybe there's a mechanism. So like Carl talked about, if the planet itself has a magnetic field, this could shield it from flares and coronal mass ejections. So maybe adding a magnetic field to the planet is something that needs to happen. Or maybe you need to start with a lot more atmosphere than you need, and the atmosphere will erode away until you're left with the right amount of atmosphere. The truth is, we just really don't know if these planets have atmospheres or if they're potentially habitable, because we don't have any observations of the atmospheres of any planets around any low mass stars. So we can write papers and theorize all we want, but we really won't know until we look. And the really nice thing about studying this right now is that hopefully we'll get an answer in the next few years, because the James Webb Space Telescope, which is going to launch next year, should be able to look at atmospheres of rocky planets around these low mass stars. So hopefully I can give another talk in a few years and answer some of these questions as to whether there can be life around these low mass stars. So that's all I have today.
Thank you very much, Aurora, for this great talk. It was very, very interesting. I see we already have some questions.
Great.
So the first question is from Fahim. Does rotation change depending on a binary system?
Yeah, that's a great question.
Attached to binaries do have some impact.
Yeah, so binaries can definitely have an impact on the star's rotation. If the star is in a really close binary, what happens is both the rotation period and the orbital period will start to sync up, which is kind of like what happens with the Earth and the Moon, where the Moon always has the same face facing us. And so, yeah, if the stars are in a binary system, their orbital period and their rotation period will be the same. And so if they're in a close orbit and their orbital period is a day, then their rotation period will also stay a day. So they'll stay spinning faster for longer.
Great, thank you. Then a question from BVD Vorn. how do you measure the strength of the star's magnetic field?
Also a really good question. So the most direct way that we can measure the strength of a different star's magnetic field is through a quantum mechanical effect called Zeeman splitting. So basically what happens is if an atom is sitting in a magnetic field, its own magnetic moment interacts with the outside magnetic field. And instead of seeing just one absorption line, you would see multiple absorption lines. And you can measure how these lines split, and that tells you how strong the magnetic field is. And so we can measure this Zeeman splitting on different stars and back out the magnetic field strength of the star.
Okay, then the next question is from Wim. What makes sun-like stars slow down spinning, and why doesn't this apply to low mass stars?
Yes, so this is an open area of research as to why it doesn't apply for low mass stars. For the sun-like stars, basically as the magnetic fields and the magnetized wind, like Carl showed with the ballerina skirt, as that slowly is pushed out into space, the star loses angular momentum. And so basically over time, the star is just going to slow down as it loses angular momentum. For low mass stars, it is completely unknown why they don't slow down the same way as sun-like stars. There's a few theories. Maybe it has to do with the structure of the low mass stars' magnetic fields not being dipolar. They might have stronger quadrupole or octopole moments, which are basically, instead of just having, a nice ring, they have lots of more complicated fields, and so they don't lose angular momentum faster. Those are just theories. It's not known is the answer.
Okay, then we have another question from Tone Fishbroth. Well, first of all, he says, awesome talk.
Thank you.
What about the heaviest stars? Do they noticeably slow down during their short life, or do they blow up before they wind down?
Actually, I am not sure. I don't know the answer to that. I don't know that much about the most massive stars. I would think that they would slow down, but I don't know what their diagram looks like for their age versus rotation period. And like the question said, they have much shorter lifetimes. And so, yeah, my answer is I don't know.
Okay, thanks. Then we have a final question from Ton asking, could a giant flare from a red dwarf create red dwarf weather on Earth? So I think that it's like as strong that like it can even get weather on Earth.
Nope, it shouldn't ever trigger like aurora or any of that type of weather on Earth. It's just so far away. Other stars are just so far away, but like the video I showed, our telescopes can pick up the flares on red dwarfs really easily. So the telescope that picked up this flare, it doesn't normally it picks up normally just flares on the sun and some other really energetic events. And they didn't actually even know that it would be able to register a flare from another star because the star is so far away. But the telescope saw it, triggered, and observed it. And so that kind of shows you how intense these flares are. But the other stars are just so far away that we wouldn't ever be able to have any sort of weather effects here on Earth.
Cool, thank you so much.
Yeah, thank you.
Yeah, the gratitude also on YouTube is really high. People are clapping and saying thanks. So I think I'll leave the closing word to Wendy.
Aurora, if you could stop sharing your screen. And I will share mine. Okay, so just as Anik has just said, thank you very much to both Carl and Aurora for coming online today and joining us virtually. We do plan to do this again in April. We usually have a meeting the last Monday of every month. Our speakers are yet to be confirmed for April, but we will let you know, keep an eye on our social media and web pages to see the exact details of when and how that will be. Yes, so thank you to Carl and Anik. We would usually present them with a lovely Astronomy on Tap Leiden beer glass. You will get these as soon as we can post them to you or see you here in Leiden. I want to say finally, firstly, thank you to everybody who's joined us. I've seen nearly 100 people at one point on the YouTube channel. That's great. And people joining us from not just Leiden, the Netherlands. We've got people from The Hague, from Katwijk, Haarlem, and Amsterdam, but also from other countries, Belgium, Germany, and UK, and even further afield from, I saw some people from Bangladesh, South Africa, and even the United States, somewhat early in the morning for them. So thank you all for joining us and supporting us in our endeavors to bring something of astronomy to you in these somewhat troubling times. And thank you for sharing a drink, a beer, or in some cases, I saw some wine or tea or cake. Yeah, thank you all too for joining us. Finally, a big thank you, as you can see on the slide here. It's a large team of people that actually makes this happen here in Leiden. So thank you for everybody for joining in and helping. Cool, and hopefully see you in a month. Good night.